basic formulation of compressible flow phenomenon. Okay, so we have understood certain parameters. What is Mach number? What is compressibility? And what is speed of sound? And basing on that, some flow classification is introduced. Now, all of it, think about this. How do we analyze the compressible flow field? What do you want to know? Behaviorally, compressible flow is known as the flow is passing as its density and temperatures, they change significantly as the velocity is changed. So what is so special about this? What are the other things that we need to know to devise something required for aerospace application? So many other things we have to understand. What is the topmost governing equation that we need to understand and apply to gas dynamic phenomenon or a compressible flow phenomenon? Think and tell me. Did you understand the point? So the whole thing is, how do you suppose how to find out temperature velocity relation? One more classification it is still pending is classification of low speed to high speed is still pending. We have classified incompressible to compressible gaseous medium. If the Mach number is less than or equal to 0.3, incompressible more than 0.3. But what is low speed and high speed? It is basing on the very definition of low speed, high speed classification, and its significant variation is percentage change in temperature of the flow field should be exactly equal to 5%. What is that Mach number? If you find out that Mach number, flow field velocity less than or equal to that particular Mach number, flow field is treated as low speed. So we don't need to worry about serious thermodynamic considerations of temperature change. Life is comfortable. So that particular Mach number onwards, if the flow velocity Mach number is changed, temperatures of the fluid medium also changes significantly. This significantly means 6%, 7, 8, 30, 40%. We have to estimate. We have to estimate this. So that's a big story. So in this process, what I want you to understand is, let us try to briefly look at, I am not going to take up the entire thermodynamics now because whatever is necessary I will be covering. Now I will talk about whatever we have learned in thermodynamics, study flow energy equation. Energy equation, always remember one point because this is not the one what most of us, we don't use it. What are the governing equations for a fluid flow phenomenon? Means, in simple language to the student, rules and regulations, principles. Tell me, behavior of the fluid. How governing equation means how fluid behaves on different accounts. Continuity equation. What it gives in simple, area velocity rule, incompressible. Newton's second law of motion, closely Bernoulli equation. It gives pressure and velocity. These, if you are using only these two things, what is the other consideration of governing equation? Mass flow rate, momentum, energy. Energy equation. So far we have not talked about energy equation importance and its presence also. Because when do we use energy? People always talk about energy equation. Bernoulli equation is not an energy equation, it is a momentum equation, it is a force balance equation. In the entire fluid mechanics, we never talked about energy equation. In thermodynamics, only energy equation is introduced. Now tell me, for a particular fluid flow phenomenon, what are the suitable governing equations depending on the flow field? Please talk about this. A general discussion. Fluid flow. In fluid flows, what are the suitable governing equations? What do you ask? So we have classification. What are the classification in Suppose with regard to, I talk about our usual fluid mechanics. For liquids, liquids alone you talk about, fluid is passing through a pipe. Okay, river flow is there. What are the governing equations we use? What are the governing equations we don't need to use? They are passive. Even if you apply, we don't know what for we apply. So liquid flow field, what are the governing equations? Moment continuity equation, mass flow rate is constant, mass conservation, right? Next one is momentum conservation. The second law of motion conservation. Only we use. We apply energy equation. You can apply, but what do you gain? Under what? Please understand, it's a serious change of thermodynamics. When do you use energy equation? Is energy equation really applicable? If I ask a question, applicable, it is useless to apply. Energy equation connects what? Okay. Liquids. For gases, what are all the governing equations? Because governing equations are chosen depending on significant change of the parameter. Significant change on a parameter. Suppose liquid flow field with the velocity, temperature changes significantly. Does temperature change significantly for a liquid flow? No. Energy equation is one which connects temperature between two stations. When temperature does not change in a liquid flow, what is the use of applying energy equation to find out a temperature at a second station by knowing the temperature at the first station? You will come out to the same value. So there is no need to apply energy equation. It is applicable. What is the use of applying it? You will get the same value. So energy equation is passive. Never say that energy equation is not it is applicable. But we don't use it because the consideration of the liquid flow is temperature is not going to change significantly. We don't need to find out the temperature because temperature is same everywhere in the flow process. Right? Gaseous medium. Gaseous medium. Now gaseous medium, so this is not our topic. So what are all these suitable governing equations for the fluid which is liquid to understand everything what is happening to the liquid? Conservation of continuity equation and momentum equation are sufficient to address every change of liquid flow. First point. Even for the gaseous medium, gases are compressible in nature, but in the last class we have classified into incompressible and compressible. Here, in the incompressible zone of the gaseous medium, what are all the governing equations applicable? What properties change significantly? Here, mass conservation is applicable everywhere for everything. Momentum conservation is everywhere. Whether there is a need to apply energy equation to find out the temperature in the incompressible medium? Is there need incompressible medium? Incompressible medium is a low speed. Low speed means temperature field is temperature is almost constant everywhere, even with the velocity change. That's the definition I gave. So even in the incompressible gaseous medium, we can manage the show with conservation of mass and momentum. Because temperature as a parameter is not going to change significantly. As long as temperature of the medium is not going to change significantly with the change in velocity, there is no need for applying energy equation to find out the temperature. Temperature is constant. That's where people should understand. Now the compressible medium is the one where gas dynamics we call, but though it is low speed, suppose compressible medium is also low speed, because I gave a clarity. This will understand. Compressible and high speed, if you call. High speed flow is a flow field in which temperature also changes significantly. Then only you have to apply energy equation. There is a meaning to apply because temperature is changing at station to station. You have to find out the temperature at second station by knowing the temperature at first station. Understand? So energy equation is passive in the fluid mechanics. Gas dynamics, energy equation will be active. Energy equation will be active. It is needed because temperature of the medium is changing significantly with the change in velocity. This is what you have to understand. So in the gas dynamics flow phenomenon, the governing equations that are directly applicable and needed are conservation of mass, conservation of momentum, conservation of energy. And remember, governing equation only not two. For any this kind of science, second law of thermodynamics is also governing equation. I'll talk about this now. Second law of thermodynamics. Second law says in which direction a process should take place. That's a rule. It always takes place from high potential to low potential. Low potential, high potential, it is not possible as per second law of thermodynamics. Second law of thermodynamics questions. It is not possible, don't do it. So, as we enter into the gas dynamics, the prominent equation that I take up to give you the important features of gas dynamics flow field is energy equation. So, steady flow energy equation of thermodynamics format, you tell me. All of you, please recall and tell me. Steady flow energy equation for an open system, actually. Steady flow energy, we call it. It's not a closed system. So we are not going to just give all the steps, but recall how many parameters are involved. Heat transfer is involved. Workflow is involved. Flow rate, flow is transferring from one station to other station. It has velocity from velocity change from one station to other station, and it has elevation difference at one station to other station. These many things are there. Temperature changes from one station to other station. So we see temperature change to how do we write this? There is a parameter called enthalpy. Enthalpy I'll talk about very clearly. So let's write the format. Q dot minus everything is time parameter is equal to H2 minus enthalpy in terms of mass is involved plus half m dot V2 square minus V1 square plus G Z2 minus Z1. If you take up a system of open system of one particular one, then you can apply at station 1 and 2. This is how it happens, and heat transfer is involved and workflow is also involved. Heat transfer can enter in effective heat transfer. Then if you write flow velocity, it takes place, and how do you combine all the parameters and under steady state. This is the one. Now, this is the thermodynamic general formula. In thermodynamics, every parameter is involved. In the gas dynamics process, why I take this is the beginning point or foundation for gas dynamics. Foundation for gas dynamics is steady flow energy equation, but not in this format. I'll tell the format. Write down. In the gas dynamics flow process, gas dynamics flow process is considered to be adiabatic. Let's say adiabatic is when there is no heat transfer involved in the process. There is no heat transfer involved in the process. And in the gas dynamics flow process, we are not going to give any work input or we are not going to extract any work output. Okay, we are not working for any machine. We are not supplying flow through a turbine or we are not drawing flow through a compressor. Then W will prevail. I'm just simply talking about flow process from one station to other station. Where is the work involved? External work output or work input, but they are not involved. It's just a flow process. Then in that case, there is no work is involved. In the gas dynamic flow process analysis, if you want to use this for a turbine, then this will come into picture. Our science is what? Our science is something, we are analyzing flow process from one station to another station. That is the only task. In between, there is no mission. No work input involved, no. So gas dynamic process is dealt with no work involved. And since it is a gas, what is the elevation difference from station 1 to 2? If it is a liquid, we can understand. Elevation difference, this load density is less, and mg z1, mg z2, they don't carry much weight or much change. So for the gas dynamic flow process, in this particular room, what is the change of pressure with the elevation in this small room? If it is liquid, considerable. So under that criteria, gas dynamic process, potential energy difference won't be there. Potential energy, some parameter may be there. Difference won't be there with the change in elevation. So that is the criteria. Then how it is simplified? I am talking about specific conditions. Specific means everything divided by mass. So how do we change the entire formula? Gone. This is also gone. Divided by mass flow rate everywhere. And here in this mass is there. M small m dot into small h1. H2 is capital H. So capital H means into mass. So I am writing for specific terms. Then it can become H1 plus V is velocity, V1 square by 2 is equal to H2 plus V2 square by 2. Look at now everywhere. Under specific terms, the steady flow energy equation under the criteria of adiabatic flow process, when no work is involved and there is no elevation difference since it is a gas, and the entire steady flow energy equation of the complete glory is now simplified as H1 plus it is specific enthalpy. V1 square by 2 H2 plus this is the one we use in the entire gas dynamics. My opening class for gas dynamics is this equation. Okay, I tell you now, this equation is already known to you in thermodynamics also. You have seen this format also. H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Everywhere if you apply, it is a constant. Like a Bernoulli. Like a Bernoulli. What is the Bernoulli equation for incompressible flow? Okay, now I tell you, this particular equation contains everything of flow process, including incompressible to compressible, supersonic, normal shock wave, hypersonic, everything is contained in this particular single equation. It is a universal equation, but it is in a closure form. It's a closure. We have to open up according to the usage. This is a powerful equation. I will show you the power of this equation in every class. Please count someone. When I want to make a derivation, I begin with this only, including hypersonic vehicle, including hypersonic flow field, including supersonic and oblique shock wave, normal shock wave, or flow through a convergent nozzle, convergent divergent. We need this. Mechanical engineer's discussion ends here. Aerospace engineer discussion begins here. They just quote this and leave it. But you see how we open for gas dynamics and aerospace applications. So we'll see one thing. Now I'll just show you what is this equation basically. This equation nature, we have to understand every time. It is applicable for what kind of processes. Please, I repeat many times. This particular energy equation format can be applicable for flow process under what conditions? Flow field must be steady. Flow field must be adiabatic. Right? Flow field must be steady. Adiabatic equation actually. Energy equation. Basically adiabatic. Because assumption is adiabatic. No workflow, that is okay. But what is the process for which it is only applicable? It is not applicable for isothermal. It is not applicable for constant temperature process. It is not applicable for constant volume process. It is applicable only for adiabatic process because Q is made 0 from the steady flow original equation. So this equation is applicable only for adiabatic process. One more thing. Any process can be two types. It becomes sometimes thermodynamical. Any process can be two types. Reversible process, irreversible process. Reversible adiabatic process, irreversible adiabatic process. In general, every process is irreversible. Ideal processes are reversible process. They are used for reference. That is the reference process comparison. Then what is the deviation to the actual reality? So this particular equation in the derivation of steady differential equation, there is no mentioning about whether it is reversible or irreversible. The same equation is applicable for both reversible and irreversible adiabatic process. Please write this and remember, applicable, valid for both reversible and irreversible. First of all, get this information. You will get clarity. This information you please keep in mind. Every time you ask me, sir, this process is reversible or irreversible. How to check? First of all, what is reversible process? You should understand clearly. I will ask you. Irreversible. This particular energy equation is applicable for, valid for both reversible, irreversible adiabatic flow process. So let me tell you the usage of this. H1 plus 2 differentiation we apply. V1 square by 2 is equal to H2 plus V2 square by 2. How do you understand this? At between any number of stations you apply, this summation is constant everywhere. Constant energy is constant, but it can only change its forms. Okay. How do I write this? I will tell you this particular equation. Using this equation, I will derive incompressible Bernoulli equation. Just look at the steps. I will derive incompressible Bernoulli equation from this. Look at this. H1 is U1 plus P1 V1. V is volume plus velocity V1 square by 2. You will understand thermodynamically what is the incompressible flow. How do I define incompressible flow as per thermodynamics? Is one more element I will talk about. We know as per fluid mechanics, incompressible flow is the flow in which density does not change with the change of velocity. But there is another property that we can talk in terms of thermodynamics with regard to incompressible flow. V1 square is equal to, what is U1? Internal energy. U2 plus P2 V2, specific volume, plus V2 square by 2. All of you please follow this. This is an important one. U1 plus P1 rho 1. Specific volume is the reciprocal of density, plus V1 square by 2 is equal to U2 plus P2 by rho 2 plus, right now there is no assumption I made. If at all this has to become incompressible flow field equation, incompressible means as per rho 1 should be rho 2, only single row. Okay, substitute. Incompressible I am applying. I want to transform into incompressible equation. We will see what kind of equation it is generating if I use energy equation. Incompressible. So U1 plus P1 by rho plus V1 square by 2 is equal to U2 plus P2 by rho plus V2 square by 2. Two differentiation I am applying. V1, V2 are velocities. P1, P2 are pressures at each station. Rho is density, constant throughout. Now density constant field I am talking about. U1 is equal to U2 if I make it. Internal energy change won't be there in an incompressible flow field with the change in velocity. Because incompressible flow field density also does not vary and temperature also does not. Internal energy change is reflected only in terms of change in temperature. Incompressible flow field, do you think temperature changes with velocity? That will happen at high speed. In the incompressible medium, both temperature, both density, temperatures, both are invariant with the velocity. So in the incompressible flow medium, internal energy is constant throughout the flow field with the change in velocity. That is one more point. Then what is the final equation? P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2. Multiply whole thing with G. P1 by rho G plus V1 square by 2G plus is equal to P2 by rho G plus V2 square by 2G. If you add the elevation, this is incompressible Bernoulli equation. This contains everything. That is why it is more often confused Bernoulli equation as energy equation because of this situation. Because this has been derived from energy equation. This has not been derived. This is applied for incompressible flow field. It is becoming momentum equation. If you apply energy equation to the incompressible flow, energy equation is converted into momentum equation. How many steps are required to make incompressible Bernoulli equation in gas dynamics class? 2 steps. That is the power of energy equation. So this contains incompressible medium also. It is now, this is an important step. Incompressible Bernoulli equation we derived. The moment I derive incompressible Bernoulli equation, there is something called compressible Bernoulli equation. That also we'll do it now. Write down. This is called, don't write G terms. P1 by rho. So P1 plus half rho 1 V1 square is equal to P2 plus half rho 2 V2 square is equal to, it is incompressible Bernoulli equation. We have converted energy equation into incompressible Bernoulli equation. How do you see the whole discussion? Think about this. From this I opened up this. From this I will tell you what is the suitable format of energy equation into compressible Bernoulli. Remember one thing, energy equation only when you arrange it differently, it is called different, it is called a different equation. Otherwise everything is originated from this energy equation only. When you know this completely, you will understand everything of gas dynamics in a systematic way. For everything, background is energy equation. What is the background of incompressible Bernoulli equation? Energy equation. What is the compressible Bernoulli equation? So compressible Bernoulli equation. We'll make few steps. V1 square by 2 is equal to H2 plus V2 square by 2. H1 Cp T1 enthalpy plus V1 square by 2 is equal to Cp T2 plus V2 square by 2. Recall your perfect gas equation. P1 is equal to rho 1 R T1. P2 is equal to rho 2 R T2. What is T1? Cp P1 by rho 1 R plus V1 square by 2 is equal to Cp into what is T2? P2 by rho 2 R plus V2 square by 2. Now take up the Cp and capital R. What is Cp in terms of specific heat ratio? Cp minus Cv for perfect gas is equal to capital R. Gamma equal to Cp by Cv. Specific heat ratio. Combine them. What is Cp by capital R? Do this exercise. If you take Cp common from this, 1 minus Cv by Cp is equal to capital R. Cp is equal to Cp into 1 minus 1 by gamma is equal to capital R. This becomes Cp into gamma minus 1 by gamma into is equal to capital R. Cp equal to gamma R by gamma minus 1. Should be substituted here. Isn't it? Cp equal to gamma R by gamma minus 1. What will happen? Gamma by gamma minus 1, P1 by rho 1. R get cancelled away. V1 square by 2 is equal to gamma by gamma minus 1 P2 by rho 2 plus V2 square by 2, so on. What is incompressible Bernoulli? P1 by rho 1 plus V1 square by 2 is equal to P2 by rho 2. Similar, only additional term is there. That is why this energy format in terms of pressure and density and velocity are called as compressible Bernoulli.